Have you ever wondered why database design is so crucial in the IT world? Let's demystify this together. At its core, database design is about creating a logical and physical structure to store and manage data. But it's not just about storage, it's about doing it efficiently and effectively. Think of it like a library. Without a system, finding a specific book in a library would be like finding a needle in a haystack. Database design is that system for data. It organizes data in a way that allows us to retrieve information quickly and accurately, akin to how a library organizes books for easy access. Data integrity is another key aspect of database design. It ensures that the data stored is accurate and consistent over its entire life cycle. That's like making sure the same book doesn't appear in different genres or under different authors. Security is yet another cornerstone of database design. In this era, where data breaches are increasingly common, a well-designed database protects sensitive data from unauthorized access, much like a library would protect rare books in a special collection. Performance is also a significant factor. A well-designed database is like a well-oiled machine. It can handle large volumes of data and complex queries without breaking a sweat, ensuring that applications and business processes run smoothly. But perhaps the most compelling reason for good database design is its role in supporting the requirements of the application or business process it serves. A well-designed database can provide valuable insights, drive decision-making, and ultimately contribute to the success of a business. So, when we talk about database design, we're not just talking about an IT function. We're talking about a critical business function. We're talking about ensuring data integrity, securing sensitive information, enhancing performance, and supporting business requirements. So, a well-designed database isn't just an IT asset, it's a vital business tool. But how do we go about designing a database? Let's break down the process. First and foremost, we need to conduct a requirements analysis. This is a critical initial step where we gather requirements from all relevant stakeholders. These may include data requirements, functional requirements, performance requirements, and security requirements. We need to understand the purpose of the database, what it's intended to be used for, and the types of data it will store and manage. Once we have a clear understanding of the requirements, we move on to the conceptual design phase. Here we develop a high-level data model that represents the structure and relationships of the data within the database. Techniques such as entity relationship diagrams, or ERDs, are commonly used to model entities, attributes, and the relationships between them. The focus at this stage is on understanding the business domain and defining the entities, attributes, and relationships that will be represented in the database. Next comes the logical design phase. This is where we translate the conceptual data model into a logical one that can be implemented in a database management system, or DBMS. We define the tables, columns, data types, constraints, and relationships based on the conceptual model. Then we normalize the data model to minimize redundancy and improve data integrity. This involves following normalization rules such as first normal form, second normal form, and third normal form. These are the initial steps. But there's more to it. In the following scenes, we'll dive deeper into the physical design, normalization and denormalization, indexing and constraints, security design, and testing. All these elements play a crucial role in ensuring we have a well-designed database that serves its intended purpose efficiently and effectively. So stay tuned as we continue to demystify the process of database design. With the logical design in place, we now move to the physical aspect. The physical design of a database involves creating the storage structures and access methods necessary to efficiently store data on disk. This process includes defining the database schema, which encompasses table spaces, data files, indexes, and partitions. Factors such as data distribution, clustering, indexing strategies, and partitioning are considered to optimize performance and scalability. Now let's delve into the concept of normalization. Normalization is a systematic approach to designing tables to minimize data redundancy and avoid unnecessary data anomalies. It involves applying a set of rules known as normal forms. First normal form, or 1NF, requires that each column of a table have a unique value. Second normal form, or 2NF, demands that every non-key column be fully functionally dependent on the primary key. Third normal form, or 3NF, insists that every non-key column must be non-transitively dependent on the primary key. On the other hand, denormalization is the process of consolidating data from multiple tables into a single table to improve read performance. While normalization is about data integrity, denormalization is about balancing the need for integrity with the need for speed and efficiency. It is important to note that denormalization is not a remedy for all performance issues, and it should be used judiciously, as it can lead to data anomalies and increased storage costs. So, you see, the physical design of a database is not a one-size-fits-all process. It requires a delicate balance between the need for efficient data storage and the need for fast data retrieval. And this is where the concepts of normalization and denormalization come into play. They help us strike the right balance, ensuring that our database is not only efficient and scalable, but also robust and reliable. Physical design, normalization, and denormalization lay the groundwork for our next steps. Now that we have our basic structure, it's time to focus on performance. When it comes to performance, one of the key tools at our disposal is indexing. Indexing is like the contents page of a book, but for our database. It allows the database management system to find and retrieve data much more quickly. Imagine trying to find a specific chapter in a book without a contents page or an index. It would be a time-consuming task, wouldn't it? The same applies to databases. Without indexes, the database management system would have to scan the entire table to find the data it needs. This can be a slow process, especially for large databases. But like all things, indexing comes with its own considerations. Every time data is added or updated, the index needs to be updated too. This can increase the time it takes to write data to the database. So when designing indexes, it's a balancing act. We need to consider which columns are frequently used in queries for filtering or sorting data, and create indexes on these columns to improve query performance. Now, let's talk about constraints. Constraints are the rules enforced on data columns in a table. They ensure the accuracy and reliability of the data in the table. For example, we can use constraints to ensure that a column contains unique values, or that it doesn't contain null values. Constraints can also be used to establish relationships between tables, such as foreign key constraints. Defining constraints is a crucial step in the database design process. It helps to enforce data integrity rules, ensuring that the data in our database is consistent, accurate, and reliable. Without constraints, our database would be like a city without traffic rules. It would be chaos. So, to sum up, indexing and constraints are two key tools in our database design toolkit. They help us to ensure that our database performs efficiently and that it maintains the integrity of our data. Indexing and constraints are key to ensuring our database performs efficiently and maintains data integrity. Our database design wouldn't be complete without considering security and testing. As we delve into the world of security design, it's crucial to understand that safeguarding our data is of paramount importance. The security design phase of database design is all about implementing measures to protect sensitive data and ensuring that only authorized users have access to it. How do we do that? Well, we start by defining access controls. These controls determine who can access the database and what actions they can perform. Next, we need to establish authentication mechanisms. These mechanisms are used to verify the identity of a user before granting access to the database. It's like a bouncer checking IDs at a club, but a bit more complex. After authentication, we move on to encryption methods. Encryption is like a secret language that only you and the database understand. It scrambles the data into a code that can only be deciphered with a special key. This ensures that even if someone unauthorized gets hold of the data, they won't make heads or tails of it. Lastly, we implement auditing features. These features keep a log of all activities performed in the database. It's like a CCTV camera for your database, providing an extra layer of security by tracking who did what and when. Now, after we've designed our database and put all these security measures in place, we can't just sit back and relax. We need to test our design. Testing is a critical step that helps validate the functionality and performance of the database. It's like a dress rehearsal before the big show. We create sample data, execute test queries, and ensure everything is working as intended. Testing also helps identify any areas that may need optimization. Optimization is the process of tweaking the database design to improve its performance. It's like tuning a car for better speed and efficiency. With security and testing in place, we have a well-designed, efficient, secure, and high-performing database. And that, my friends, is the beauty of a well-thought-out database design. Database design might seem complex, but it's an essential part of managing data effectively. It's a journey that begins with a thorough requirements analysis, understanding what the database aims to achieve, and the types of data it will handle. This insight is then transformed into a conceptual design, a high-level blueprint of the data structure and relationships. The journey continues, translating this conceptual model into a logical design, ready for implementation in a database management system. It's here that we ensure data integrity and performance through normalization, and if necessary, denormalization. We then dive into the physical design, considering storage structures, access methods, and performance optimization. Indexing and constraints are essential components, improving query performance and ensuring data integrity. Finally, it's all about testing and optimization, ensuring our database design meets its intended functionality and performance. A well-designed database is a powerful tool for any business, so the next time you come across a database, you'll know what went into its design.